Okay. Last time we were right in the middle of a proof. And so we're going to take up today right where we left off last time. And if you recall, we had begun looking at chapter 4 about how to prove theorems concerning implication. And what we were doing at the end of class last time is we were proving 4.3 monotonicity of and. Now, do you remember the technique that we said we were going to use? You know, whereas before, if you have a theorem of the form, if you have a theorem of the form P equivals Q, you could start with one side and get it to the other side, or you could start with this side and you get it to this side. But what did we see last time that we're going to do now? Implication. Yeah, you can have it. Yeah, suppose now we have something like P implies Q. Now what we're saying is that because of mutual transitivity, it's possible to start with one side and get it to either start with the antecedent and get it to imply the consequent, or you could start with the consequent and get it to follow from the antecedent. Now, so which technique are we using to prove 4.3? We're proving 4.3, and over here, this is what we had on the board last. Oh, sorry, we're not proving 4.3. Wait, are we? I'm sorry, we're proving 4.2. 4.3 is, you're going to prove 4.3 for me in your homework assignment. So looking at 4.2, how did we start with 4.2?
3.57.
Well, right, but that's correct. That's what we did with the first step, but what are we starting from?
The bigger side.
Yeah, we're starting from which one? The antecedent or the consequent? We're starting with the consequent. So we're starting with the consequent. The consequent is P or R implies Q or R. So what we had here was P or R implies Q or R. And then here we have a sequence of equals by 3.57 this, equals by this, equals by blah, 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 this. Eventually, down here, there's going to be a what?
Implies or follows from?
There's going to be a follows from, and what we want to eventually get it to is what?
The other side.
Which is? P implies Q. So does everybody understand the program here? What we're going to do is we're going to have a follows from, and we're going to end up with P implies Q. Does everybody, do you remember what we did, how we did that? And remember, at the end of class last time, we had this really tricky little step. Do you remember that?
Yeah.
Because what happens is disjunction distributes over equivales. So if you have P or Q equivales Q or R, you can take this or R and you can put it here, and then you can take the or R and put it here. Yeah? Are we good?
We did the reverse of that.
Yeah, it's factoring out. It's like in algebra what you would call, it's called factoring. Basically what we're doing is we're factoring out the or R. We're factoring out the R with the or. Remember that? Okay. Does anybody see what we should do now? What are we trying to get this to? We're trying to get this to P implies Q. Does anybody see anything here?
Code implication?
Yeah, I think we should use an implication.
As in the P or R equals Q turns into P implies Q.
Right, which one is that?
I forget.
Well, I think we used it here once before, didn't we, in the very same proof?
No.
Well, I mean, what did we start? What did we start? I mean, how did we start here?
Definition of implication. That's what it is.
Yeah, which one?
Yeah, 357.
357, 3.50. Are you with me?
Yeah.
Okay, so we use 3.57 to go from here to here. Well, let's use 3.57 to go from here to here. Okay, so this equals by So this equals by 3.57. So what'd you say should go here now?
P implies Q.
P implies Q or R. Okay, now if anybody can tell me the next step, I'll be very impressed.
No idea.
What do you think the next step is?
You just get rid of the full R.
Good question. How do you get rid of the or R? Oh, did you?
You just, never mind.
Yeah, how do you just, because what we want this to be eventually.
3.69.
Huh? Oh, what's 369? What is it?
P or Q implies. Oh, never mind.
Oh,
My bad.
okay.
Is it some form of shunting?
Wait, doesn't that work? P or Q?
No, we want to get rid of the R.
Isn't that what 369 does?
No.
Oh, no.
P
Get rid of
replaced
the
by
P.
R.
Yeah, so that's not quite. How do you get rid of stuff with imply? How do you?
Can't you, like...
Cameraman knows.
Yeah, he's over there. The cameraman's over there grinning from ear to ear because he knows. And say it again. What? Are you looking? Did you have an idea? Oh, come on, you guys.
What? It's not common sense.
Yeah. Now remember what is our little what technique are we using here? Equals. What's going to be one of these symbols?
Follows from.
Ah.
Follows from.
And which ones let you get rid of stuff when you use implies or follows from?
It's just losing me.
Yeah, I am. Oh, come on. These ones you should. This
Your
one.
hints are just really
These are really roundabout hits.
Axiom comes.
so used to using equals. It just doesn't.
Yeah. We're used to. Yeah, we have to get in a different mindset.
Oh,
We have to get in a different mindset.
yeah.
Here, you're. Oh. Ah. What? Whoa. Well, would it be strengthening? You're suggesting? You're really warm. You're almost there. Come on, you guys.
Oh, I see it.
Oh, he sees it.
Weakening, strengthening D.
Which? No, I don't think it's D, but you're really close. You're so close. You're dancing right around it. Huh? E? I don't think so.
It's B, isn't it?
Aha!
What?
What is B? Strengthening the Oh, no. Sorry. Oh, whoa.
That's
Fail.
conjunction.
Oh, I'm sorry. Did somebody before say it was A?
No, but it is.
But it is.
Wait, what?
Yeah, no, I thought somebody said somebody said weakening, strengthening. It's weakening the consequent, isn't it? What does 3.76a tell us? It says that P implies P or Q, right?
Oh.
So look at what that says. It says P or Q follows from one of them.
Yeah.
Are you with me?
Yeah.
It says P or Q follows
Q
from.
implies P or Q or R.
Yeah.
U
Well,
replaced by P implies Q.
yeah. So,
Got it.
huh? So it's weakening the consequent because P or Q. What weakening the consequent says is that P or Q follows from P. In other words, by symmetry, it can follow from either one, right? Okay. So what do we have here? We have this or this. So what does this or this do by 3.76a? But now what do I put here? Not equals, but what? Follows from. See how that works? Follows from by 3.76a. Now, do I have to say with whatever?
You don't have to.
I mean, it follows from it.
P replaced by
Yeah, with P. Yeah, with PQ.
P replaced
PQ. Yeah, PQ replaced by P implies Q R, right? But that follows from what?
P implies Q.
P implies Q. And now what do? Do we say which is?
No.
No, because what did we do? We started with one side and got it to follow from the other side.
So we're done.
So we're done. Boom.
That was really cool.
Counterintuitive.
Is that slick or is that slick?
I think it's slick.
You can give us any other option.
Now, well, but what I'm saying is that now that we have this technique, we can use, before we did this, we learned these techniques, anytime we wanted to prove an implication, we had to do the whole thing. Now we can do it by starting with one side and getting it to the other. And we can either start with the consequent and get it to follow from the antecedent, or we can start with the antecedent and get it to imply the consequent. Either
You can
way.
always just prove them by using equals the whole way, right?
Well, but then you'd have to,
To get it equal.
then you'd have to, oh, well, yeah. But this gives us an alternate way. And so what I've done for your assignment, for your homework on Thursday, I've specified that you, so that we can learn this technique, specified that you use this technique of starting from one side and getting it to the other. Okay? Now, we need to talk some more about this concept of monotonicity. Because, and I will tell you right off the bat that I had a conversation with the author of the book once, and I was telling him about my experience using his book with monotonicity, and he said, yeah, he said he admitted that, and they were, at one point in time, they were planning on doing a second edition. I think that kind of fell by the wayside, but he said, yeah, in the second edition, we want to change how we present monotonicity, and he agreed that it was kind of a weak point in the coverage in the book. So I want to show you some material that's not in the book now about monotonicity, because it's an important concept. So here's first of all, let's take a look at what monotonicity is again. We just proved 4.2 monotonicity of or. It turns out that you can prove 4.3 monotonicity of and. And what it says, if you take a look at the structure of it, what it says is that if P implies Q, it says that P implies Q, or let me see it, if P implies Q, it follows that P or R implies Q or R. Now just think about that for a minute. If P implies Q, then P or R implies Q or R. And similarly, if P implies Q, it follows that P and R implies Q and R. So what it says is that if you know that P implies Q and you have an expression with that P either in a disjunction or a conjunction, that the whole thing implies the whole thing. Do you see what I mean? Now here is what I want to demonstrate. It's how to use monotonicity, because we're going to use this monotonicity several times, I mean, in the future, and we don't use it like, it doesn't come up, like on just about every proof from now on, but it does come up several times. And whenever you, and I always have a hard time getting people to understand when you must use monotonicity. So this is going to be how to use monotonicity. Okay, and these examples I'm giving you are not in the book. So let me first give. I wanted to do two examples, and the first example is this. Suppose that you have, and this is just going to be a direct one. Suppose that you have P or R. Now what I mean by suppose you have P or R, suppose you're doing a proof, and you have this equals this equals this equals this equals because of this, that equals because of the other, and at some point in your steps going through here, you have a P or R. You have a P or R as, you know, in one of the steps, okay? So suppose you have P or R and you know that P implies Q. All right? So suppose you have this as one of the steps in your proof, and you know that P implies Q. All right? Then here's how you use monotonicity. You use monotonicity like this. So here it goes. You've got P or R. Right? As, you know, so this is dot, dot, dot. You know, this is part of the...
For the proof, you end up with PR.
Yeah, suppose that this is dot, dot, dot. So suppose you're going in some long proof, and at this point you've got this, right? For some, and suppose, okay, now what can you do? Now what can you do? You can say P or R does what? You can say P or R does what? It implies by what hint? By the fact that what? Yeah, by the fact that P implies Q. By the fact that P implies Q and monotonicity.
In what instance would we know that P implies Q?
Well, it's hard for me to give an example until we get to, I mean, an example in a full-fledged proof until we actually get to one.
Sure.
But you'll see, and yeah. But this implies, and the hint is P implies Q and monotonicity. And which monotonicity? 4.1 or 4.2 or 4.3? And monotonicity 4.2. You know that this implies what?
Q or R?
Q or R. And then you can go on doing your proof. Now, I want everyone to understand what's going on here. Okay? Look. In 4.2, this is 4.2 with what does 4.2 have in it? Well, anyway. Which implies, in 4.2, which implies is this one?
The middle one.
The first one. Oh wait, no. I think it's the last one.
It is?
Yeah, he's right. It's the last one, isn't it? Is it not?
What happened to the middle one?
Good question. What did happen to the middle one?
Didn't you take it away whenever you...
Yeah, how, yeah. This Whoa, wait, maybe, is it the last one?
It has to be.
P, because we are claiming what?
Implies Q or R.
'Cause, yeah,
Yeah, what we are saying is that P or R implies Q or R,
Yeah.
right?
I think that was the last one.
So,
That's what you're doing.
Yes, we are saying P or R implies, because after all, here we have P or R. We know that because P implies Q, we know that P or R implies Q or R. But hey, are we missing one of the implies?
Doesn't it drop maybe? Because like, you know when you substitute
Because
equivals, the equivals drop?
yeah. See, this which implies is this one?
That's the first one.
That's the first one, yeah?
the whole thing is an implication.
You're right. The whole thing.
Because there's no other way to show it. You just put like it implies at the top before we even put P or I.
What? Say that again?
Like, as if we had like a step before P or R. You just put like implies above it. Because that's what knowing that P implies Q does. Because it's like P implies Q implies P or R implies Q or R. It's not supposed to.
Well, maybe it's because we know that this is true. I mean, no, we don't. Because we might be starting with one side and getting it to another side, so we don't know that that's. But at this point, I mean,
You're assuming the antecedent to be true, so therefore the right side is true. And then you can assume that that is true, and therefore it follows that the last part is true. By the implication.
Yeah.
so is everybody comfortable with this? I mean, how it works?
Can you say you have, what if you have more stuff besides the P or L?
Yeah, that's a good question. Now,
Or Z? Can you just use it?
okay, yeah, look, if this were P or, so the question is, if this were P or R or Z,
P or Z?
this would be or Z, but in that case, the R would be, this R would be R or Z. In fact, that was like my next example. Are you with me?
Yeah.
So that one was a direct one.
That way you can really do any P, like P or anything.
Well, as long as those other ones are either disjunction or conjunction.
But I mean, you could have anything.
Well, could you do it one step at a time?
You could have P or anything, or P and anything implies Q or anything.
Yes. Yes.
S or T or V or.
That's wild.
Yeah. So here, let me do another example that is a little bit more complicated. Suppose you have, here's another example. Suppose you have the expression, well, actually, this is what you just said. Suppose you have the expression Q and R or S. And you know that R or S implies P and Q. Suppose you know that. Then you can use monotonicity as follows. Then you can use monotonicity as follows. Okay, so now we're coming down here, boom, 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 and suppose you've got this Q and R or S. Q and R or S. Now, so what does this implies by the fact that what? By the fact that what?
That R S implies P or Q.
Yes, that R or S implies P and Q, and what? And which monotonicity this time? 4.2 or 4.3?
3.
4.3 because this is an and, right? And monotonicity 4.3, what? Say it again? Yeah, Q and P and Q, etc.
I understand that when you're doing step by step like this and you know like it's coming and we've been forewarned, can we do it in do a proof where we have like other steps?
Yeah, I think I don't have a complete proof where this would come into play right now, but we're just learning about monotonicity now, and the first time it happens, when we do a proof, I'll show you. I'll show you then. But I can't come up with one without going a little far afield here. So, but you understand these steps. I mean, you understand the fact that this implies this means Q and this implies Q and this. You see what I mean? It's the same idea. It's the monotonicity idea, right? Because here you have a conjunction. You have Q and this. Well, if if the R or S implies this, then Q and this implies Q and this. So now, okay, so again, which implication is this one? It's the last one, yeah, because we're saying this implies this. But the only reason we know that is because this implies this, right? So this is the P, this is the P, and this is the Q. In fact, this is this is monotonicity 4.3 with what?
Symmetry.
Well, yeah, and symmetry, right? But what is here? If we were to write out 4. Here, maybe we should do this. And monotonicity 4.3 with what?
Q replaced by R and S and P and Q.
Okay, so what do we have in 4.3? P, Q, and R? With P, Q, R replaced by what?
R, S, P and Q.
R, say it again?
R or S.
R or S,
P and Q.
P and Q, Q. Is everybody, are you guys getting this? Yeah? Because, what we're saying, yeah. The thing that we know is that this one implies this one. So the thing that we know is that P, so this is the P, this is the Q. Yeah? Yeah. So does everybody see how that works? Actually, I have a theorem here that I know that's going to come way later, where this is going to come into play. All right. So that's the main thing about, and I'm sorry that I don't have a complete proof or where we would use it, but it's going to come up. And when it comes up, I guarantee you what's going to happen. I'm going to say, now you remember no, you got to use monotonicity. You remember monotonicity? And we'll have to remember this, but it might be tricky to remember in my experience. Okay. Now, the next proof technique that we're going to learn, and I don't think you have a, no, we're not going to do case analysis yet. And I don't think you have a homework assignment on this one for Thursday, but I think you do on Monday. Let's take a look at, now the remainder of chapter 4, consists of these different proof techniques. Okay? And in the same way that what we have learned, all of chapter 4 is about proof techniques. So what we're doing here with these implies and this mutual transitivity and stuff is we're showing different ways to set up our proofs. So in the beginning we started with the way to prove something true is you get it to be equivalent to a previously proved thing. Then we said, okay, but if it has an equivalence, instead of doing that, you can start with one side and getting it to the other. Now we're saying that if you have an implication, instead of starting with the whole thing and getting it to a previous one, you can either start with the antecedent and get it to imply the consequent, or you can start with the consequent and get it to follow from the antecedent, right? Now there's some more. We're going to do some more of these. Now this one, 4.4, is the next proof technique that we're going to learn. And 4.4 is called assume the conjuncts of the antecedent. Now, here's the thing about assuming the conjuncts of the antecedent. Well, first one little small note. If you look at your, do you have your equation sheets? If you look at 4.4, I have actually made a change here. I've made an addition here that's not on your equation sheet. As I go through this material each year, I catch stuff that I should have put in, and I have added a sentence here. So let's take a look at what 4.4 says, and you might want to add this little item to your equation sheet. It says, the technique is called assume conjuncts of antecedent. and it says to prove P1 and P2 implies Q, assume P1 and P2 and prove Q. And this next little sentence is not on your equation sheet, but you might want to put it there. It says you cannot use textual substitution in P1 or P2. Okay? And I should have had that in, but I just recognized that that needs to be in here just the other day, so I went ahead and stuck it in. So if you ever download this from the internet, you know, it'll be corrected. It'll be the corrected one. And I changed it on my slides here. Okay, now this is a very interesting technique because it seems kind of like magic. So this first thing I want to say. So here, this is called assume conjuncts of antecedent. Assume conjuncts of. Okay, so first thing we want to say is this: how many conjuncts in the antecedent do we have in 4.4? Do you remember what a conjunct is? Do you remember that terminology? Yeah, there are two conjuncts. What are the two conjuncts? P1 is one conjunct and P2 is the other conjunct. Okay.
It's what's in the conjunction.
Yeah. This is a conjunction, right? So if you have an and you have something on this side and you have something on this side, this is one conjunct. This is another one. Now, here's the thing. I only put it here for 2 because I didn't want to do ... But what do you suppose? What's another? If it works for 2, it also works for what? Yeah, 50 or 3 or 4. I mean, so you could say P1 and P2 and P3. If you want to show that this implies Q, then you would use the same technique, only instead of just having 2 conjuncts, you could have 3 or 4 or 5 or, like you said, 50. But what else? Well, yeah, but what's another number that would work? Not only 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 8, but what else?
False.
1. Are you with me?
No.
So it's kind of a misnomer here, because if you say assume the conjuncts of the we're going to call this assuming the conjuncts of the antecedent, even though there's only one, even though there is no conjunct here.
Well, P equals P and P, so.
No, that wouldn't be a conjunct. It'd be P and true.
Yeah.
Would be, yeah.
True, you can let P.
Yeah, and then but assuming true is, yeah, and then P. All right. So does everybody understand that even if we use this in the case where there is only one thing here, we're still going to call it assuming the conjuncts of the antecedent, even though there's really no conjunct there. But does everybody get this? Get that little detail? Okay. So I have it here for 2, but it works for 3 or 4 or 5 or even 1. Okay, so that's the first. Okay. So that's the first thing. Now, here's how this works. It says to prove P1 or to prove P1 and P2 implies Q, assume P1 and P2, and it says and prove Q. So here's how it works. You start with Q. All right? And here's what you have to remember when you do this. When you use the technique of assuming conjuncts of the antecedent, you have to get this to true. Because we're proving this, what we're doing is we are proving this as if it were a theorem. Are you with me? We are proving this as if it were a theorem. So we're going to have to either get it down to da-da-da-da-da. which is a theorem, or you can say da-da-da, true. And we know that true is a theorem, previously proved theorem. Are you with me? So you've got to get this to true. Okay? So it would work like this. Suppose we know that Q equals by some theorem. I'll do a specific example in a minute, but let me just do it in general here. R, okay? And then you can say equals, now watch this, equals, and now here's what you can do. You can put P1 here.
What?
What? You can put P1, you can use P1 as if it were a theorem. Whatever P1 is, you can put that, you can use it in a hint as if it were a theorem. Okay? Are you with me? And say that gives you S, all right? And then suppose that equals by, I don't know, some other theorem. Some other theorem. Because, we always use previously proved ones here, yeah? Some other thing. Suppose that equals T. And then what you can do here is you can say equals, and here what can you do? You can put P2 here as if it were a theorem. And get...
Kind of just substitution in itself.
Well, it's whatever those conjuncts are, you can treat each individual conjunct as if it were a little theorem. You see what I'm saying?
So if you had like P equals Q and Z equals R, then you could use P equals Q as a theorem and then...
Well, now, this is only with implies. You have to have, this is with an implies. Yeah. Yeah, if you have some expression and some other expression implies whatever, you can take each one of those individual expressions and use them as if they were individual theorems in the steps and start with the consequent. And what happens is if you use those as theorems and you get this to be true, it's the same as that. Okay, hold on. Okay,
Three different theorems?
yeah.
And 50.
And you don't have to use.
Or even one, and you don't even have to use them all. Okay, yeah, that's another interesting thing. Okay, but anyway, let's say that this this equals U, and then suppose this equals by some theorem. Yeah. Theorem true. Then boom, you're done.
That's crazy.
Because you don't have to say which is a previously proved, because true is a previously proved.
Yeah, how does that prove that P?
Yeah, now let's think. Yeah, now that's a very good question. Why does this work?
Why is that okay?
Why is that
We're
okay?
assuming it to be true.
Why is that okay? Now let me tell you that on some of these previous proof techniques I was able to go through and show you. Well, because if you have a proof like this, it's the same steps as if you did a proof like this the normal way, and therefore these two proofs are equivalent. To show that this actually works is very tedious, and
Let's do it.
we don't have time. It's a very involved. It's kind of an involved, tedious thing to do in general, and trust me, you'd get bored.
Now, can you mix, if S implies T by some other theorem, can you have S?
No. Look, the question is, look, this has to be equivalent to this. You cannot have implies in here anywhere. Was that your question? Does everybody hear that? You cannot have, these cannot be implies. No, you can't have an implies in any one of these.
Equal true.
Yeah, because what it says is you have to prove Q. But now, doesn't anybody think that this is reasonable? I mean, don't you? I mean,
You're not showing me why it makes sense, so yes, I think it's reasonable.
You don't think it's reasonable? Well, does anyone else think this is a reasonable thing?
Like, is reasonable?
Yeah, don't you think it's reasonable?
We're assuming P1 and P2 are true, right?
Yeah, this,
So then we're just using theorems and axioms and true things to prove something to be true. And so yes, I think it's reasonable.
But we're
because-
assuming that they're true.
well, I know, but the whole thing that we're trying to prove is
Based
if
on that
P1 and P2,
Okay, all right.
then
That's
Q.
like a thingy.
A thingy.
Implication.
Meta theorem.
Wait, so do you have to use,
If
you have to use
P1
P?
Look, look,
If
Use
P1 and
those as
P2,
theorems?
P2 are true, then Q. So then we can assume they're true to see if we can get Q.
yeah, because what we're saying is, look, if P1, huh?
You have to use those as
It's like an
theorems.
inference rule.
You don't have to use all of them. no.
You actually don't have to use all of them.
You have to use some of them.
Well, if you're going to use I mean, if you didn't use any of them, then Q would be a theorem by itself, and I don't think we would ever ask you to. You see what I mean? If you didn't use any of them, and you could prove that Q is true without using any of it, then Q by itself would be a theorem.
Yeah, but then-
And that would be an illogical thing for
The
us to.
statement wouldn't be a theorem, because you're trying to prove the statement P and P1 implies
P-
Q, right?
We're trying to prove that P1 and P2 implies Q. That whole thing,
Yeah.
okay? So what we're,
If you got Q to be a previously proved theorem. then
You mean without using P1 or P2?
then it wouldn't prove that whole statement.
well, it would, but on the other hand, that would be kind of trivial because you would be proving P1 and P2 implies true, right? But we know this already, don't we know? Because isn't this something that we've done before? Oh, what? I'm saying that if Q was equivalent to true,
Yeah.
we would be doing P1, but we know this. What is this one? Implies true? Something implies true? Does that look familiar? Something implies true? Does that look familiar?
Oh, something implies true, implies
Is our, I mean,
true.
yeah,
Yeah, oh, well, that's, now I get it then, because that's why you use P1 and P2 in the theorem.
Yeah, right, 0.
Because,
which one is that, right? I'm trying to find it.
372.
72?
because that's why if you use P2 and P2 was true already, then it
Yeah.
would make sense, and Q would be, say, if P1 and P2 are both true, then Q would end up being a theorem anyway. And
Yeah, that's what I'm
that
saying.
makes sense. But if they were false, then Q would be false as well, but you would have a false implying a false, which is true.
Yeah.
I get it now.
You can prove by case analysis pretty easily.
Well, let's not muddy the waters with case analysis now, the one thing. Okay, but now, the point is, does this make sense? I think it totally makes sense because what we're saying is, let me go back to here. Because what we're saying is, we're trying to prove that P1 and P2 implies Q. Well, what we're saying is, if P1 is true and P2 is true, then Q is true, right? So you can use you can use these as if they were little theorems, but you've got to be careful. I mean, nobody ever makes this mistake, but that's probably why I failed to put that little statement in there earlier. But you can't take one of the conjuncts and do textual substitution in it like you can a regular theorem. Do you see what I mean? You can't, because you have to treat it like it's a constant, right? So you can only use P. You can't say P1 with, here, this would be illegal. You can't say P1, with, PQ replaced by blah, blah, blah. This is illegal, okay? You can't do this. You have to just use them straight away. Yeah?
Totally.
Yeah?
P1 is just one variable. That wouldn't do anything with it.
Yeah, you could do it. P1, yeah. In fact, yeah, that's...
Why would you ever use it if it's just a variable?
Oh, okay, here, let me show you. Actually, he's my plant. Okay, here, let's do this. Let's prove. So let's do this. Let's do an example.
Were you really just about to do that?
Yeah. to prove, watch this, to prove P and Q implies P equivals Q, P and Q implies P equivals Q, what do we do?
Assume P and Q,
Yeah, we prove what do we prove?
P equals Q.
We prove this, right? Okay, so prove P equals Q, assuming
You have to write that. You have to do
prove that
stuff.
prove P. Well, you have to state what you have to state, assuming the conjuncts of the antecedent, and then start with the antecedent. Okay, so prove P equals Q using P as a theorem, using P, assuming.
You mean start with the consequent?
Yeah, you start with the consequent. Prove P equals Q, assuming P as a theorem, P as a theorem, and Q as a theorem.
Can you try to assume the conjunct?
Yeah, you don't have to write this all out. I'm just doing it. Q as
Why would
a.
you ever have something equivales something else because of P?
Well,
We'll see.
yeah. Let me just work through this example. So here it is. P equals Q. All right, so we're starting with P equals Q. Now, tell me this. This equals, now watch this. So what's our assumption? So here you can say, and here whenever you use it, you should say assumption.
You have to write that?
Yeah, you need to say assumption, okay? Because we're assuming the conjuncts of the antecedent. So which one are we assuming here? Let's say assumption P. Well, if we are assuming P, then what does this?
True equals Q.
Yeah, this is true equals Q.
Oh.
Oh, because P equals true, okay.
Are you with me?
And then you do assumption.
Is that clear? And then we can say equals by assumption Q.
True equals true.
True equals true.
Equals true,
Which is replaceable.
Yeah, which is 3 point what?
5.
Yeah, which is
P replaced by true.
3.5 reflexivity. Boom.
We're pretty fun today.
I get it.
Huh?
That was cool.
So that statement we just proved. So
Well, so now what we did is we proved this whole thing, that P and Q implies P equals. Now think about how hard it would be to do this.
kind of difficult because that's only like 2 steps.
Using conjunction.
It is like that is kind of like
equivales
magic.
It is kind of like magic, isn't it? But I mean, don't you agree that if that P and P,
I get it now.
yeah,
Because if they're not, if P and Q weren't true, then there'd be no point in
Then
having.
you just have false implies false,
Yeah.
which is true.
okay. Now let me close with this note. What we're going to do from now on is we are going to use, technically speaking, we can only use these new proof techniques after chapter 4. What we're going to do, though, is we're going to go and apply them to some previous ones. And I'm going to call these reproofs. And they're not really legitimate proofs because we're using later material to prove something that, we're actually assuming something that went later. So they are not genuine proofs, but they make such good exercises, and it's very difficult to come up with a whole new set of theorems. So we're going to go back and reprove previous theorems using these proof techniques, but you should know that these are not legitimate proofs, they're just good exercises. Okay, so when I say reprove using this technique, keep that in mind. Okay? All right, good deal. See you Thursday.